Class 11th, Subject Physics, 6th chapter, Mechanical Properties of Solids. Mechanical Properties of Solids. From the chapter, let us see Numericals from exercise. Numericals from exercise. Let us see numerical number 9, which is given as a steel wire having cross-sectional area 1.2 mm square is stretched by a force of 120 Newton. If a lateral strain of 0.1455 mm is produced in the wire, calculate Poisson's ratio given that Y for steel is equal to 2 into 10 raised to 11 Newton per meter square. And therefore for this numerical given data is area A is equal to 1.2 mm square, which will be written in terms of meter square as 1.2 into 10 raised to minus 6 meter square. Then force F is equal to 120 Newton. Then lateral strain is given, that is 0.1455 mm, which will be converted into meter as 0.1455 into 10 raised to minus 3 or 1.455 into 10 raised to minus 4 meter. Then Young's modulus Y for steel is 2 into 10 raised to 11 Newton per meter square, and we have to find out Poisson's ratio sigma. Now Young's modulus Y is equal to FL upon A into delta L, FL upon A into delta L. Therefore linear strain, that is change in length per unit original length, delta L upon L is equal to F upon AY, F upon AY. Therefore delta L upon L will be equal to 120 upon 1.2 into 10 raised to minus 6 into 2 into 10 raised to 11. Simplifying this, we will get 100 upon 2 into 10 raised to 5. That will be written as 50 into 10 raised to minus 5, which will be equal to 5 into 10 raised to minus 4. Now Poisson's ratio is the ratio of lateral strain to the linear strain, and therefore Poisson's ratio sigma will be equal to lateral strain upon linear strain, that will be equal to 1.455 into 10 raised to minus 4 divided by 5 into 10 raised to minus 4, which comes out to be 0.291, which is the required answer, that is Poisson's ratio equal to 0.291. Now let us see numerical number 10, which is given as a telephone wire 125 meter long and 1 mm in radius is stretched by a length of 125.25 meter when a force of 800 Newton is applied. What is the value of Young's modulus of material of wire? So given data is length L is equal to 125 meter, radius R is equal to 1 mm, that will be equal to 1 into 10 raised to minus 3 meter. Then L plus delta L is given 125 plus 25 meter, and therefore as L is equal to 125, therefore delta L will be equal to 0.25 meter. Then applied force F equal to 800 Newton, and we have to calculate Young's modulus Y. The formula for Young's modulus Y is FL upon A into delta L, FL upon A into delta L, which will be written as FL upon pi r square, that is area of cross section of that wire, into delta L, FL upon pi r square into delta L, and therefore Y will be equal to 800 into 125 divided by 3.142 into 1 into 10 raised to minus 3 square into 0.25, which will be equal to 800 into 500 divided by 3.142 into 10 raised to minus 6 which comes out to be 4 into 10 raised to 5 divided by 3.142 into 10 raised to minus 6, which will be written as 1.273 into 10 raised to 11 Newton per meter square, and this will be the required Young's modulus for material of that wire. Then let us go for next numerical, that is numerical number 11, which is given as a rubber band having its original length equal to 30 centimeter is stretched to a length of 32 centimeter by certain load. What is the strain produced? And therefore for this numerical, the original length L1 of the rubber band is equal to 30 centimeter, then final length L2 equal to 32 centimeter, and we have to find out the strain produced in that rubber band. Now we know that strain is equal to change in length per unit original length, that is L2 minus L1 upon L1, and therefore we can write 32 minus 30 upon 30, which comes out to be 2 by 30, which will be equal to 1 by 15, and that 1 by 15 comes out to be 0.0667, which will be written as 6.67 into 10 raised to minus 2. This will be the required strain, that is 6.67 into 10 raised to minus 2. Then we will go for next numerical, that is numerical number 12, which is given as what is the stress in a wire which is 50 meter long and 0.01 centimeters square in cross section if the wire bears a load of 100 kilogram. And therefore for this numerical, given data is L is equal to 50 meter, then A is equal to 0.01 centimeter square, which will be written as 1 into 10 raised to minus 6 meters square. Then M is equal to 100 kilogram, G is equal to 9.8 meter per second square, and we have to find out stress. We know that stress is equal to force per unit area, that is F by A, but F will be equal to mg, and therefore stress will be equal to mg upon A, that will be equal to 100 into 9.8 divided by 1 into 10 raised to minus 6. Calculating this, we will get 9.8 into 10 raised to 8, 9.8 into 10 raised to 8 Newton per meter square. Now let us go for numerical number 13, which is given as what is the strain in a wire cable of original length 50 meter whose length increases by 2.5 centimeter when a load is lifted. And therefore for this numerical, the given data is original length L is equal to 50 meter, change in length delta L is equal to 2.5 centimeter, which will be written as 2.5 into 10 raised to minus 2 meter. And we have to find out the strain produced, that is strain is equal to change in length per unit original length. Putting the values of delta L and L, we will get 2.5 into 10 raised to minus 2 divided by 50. 2.5 into 10 raised to minus 2 upon 50, which will be written as 25 into 10 raised to minus 3 upon 50. 25 into 10 raised to minus 3 upon 50, which comes out to be 1 by 2 into 10 raised to minus 3. But this 1 by 2 is 0.5, so that strain will be equal to 0.5 into 10 raised to minus 3, which will be written as 5 into 10 raised to minus 4, and this will be the required strain, that is 5 into 10 raised to minus 4.